we've done all of that. Now we have to solve it. Okay? So at this point, we just put on our thinking caps of what we learned in our numerical methods class. Okay? In our numerical methods class, we learned all sorts of numerical tricks, Newton, Raphson, Gauss-Seidel, we learned about the Jacobi matrix, and so on and so forth. Okay, that is what this is doing in the background. Okay, so here it says that the continuous initial boundary value problems are discretized into algebraic equations using numerical methods. And then after that, we assemble the system of algebraic equations and solve them to get approximate solution. We are solving, remember in numerical methods, you have your domain, you discretize it, okay? And so you're obtaining discrete solutions at different points within your computational domain, okay? Versus the exact solution, which is a continuous solution at every point. So here, as you can imagine, depending on your discretization method, that would impact your solution. Depending on what solver or what numerical parameters that you are specifying, that would impact your solution. Depending on how you are generating your grade, or if you are going to do any grade transformation, that would impact your solution. Depending on whether you're using high-performance computing and some post-processing application, that would impact your solution. Okay? Depending on if I'm solving the problem on my laptop, okay, versus I'm using a supercomputer with so many computing clusters put together to solve my problem, that impacts the solution. Okay, so we have to understand the numerical methods behind the solution process so that we can accurately specify the approach to solve it. And so what are some of these discretization methods? Okay, what are some of these discretization methods in CFD? Okay, let's look at them. One of the first or more simple applications, the discretization method in CFD is the finite difference formulation, the finite difference methods. It's very straightforward to apply, and it's usually applied to a regular rectangular grid with, let's say, the x interval the same as the y. Your delta x is equal to your delta y. Okay, that is basically your finite difference method. Versus your finite volume methods and your finite element method, which basically puts together irregular meshes, okay, irregular meshes to form your computational domain. Okay? And so, really, in CFD, we can take a whole course on finite volume methods. We can even take a whole course on finite difference methods, and we can take a whole course based on finite element methods. Okay? What is the advantage of using one over the other? It all depends on the complexity of your problem. Okay? If it's simple geometry, then finite difference methods would basically be appropriate. If it's a more complicated structure, then it's best to use the finite volume or the finite element method. Finite element methods are more applicable to structural problems where you are determining stresses and strains within a structure, a structural material. Okay? Whereas in fluid flow systems, the impact of fluid forces or stresses on objects, you use either the finite difference or the finite volume approach. Each type of methods above use the same solution if the grid is fine solutions. Okay? In the limit as your delta x approaches 0, fine mesh. The limit as your delta y or your delta z approaches 0, again, yeah, that means there's the spatial discretization is very fine within the system. All these two methods collapse to the same solution. You're going to get the same results. However, like I said, some methods are more suitable to some cases than others. Finite different methods for spatial derivatives with different order of accuracies can be derived using the Taylor series expansions. Who remembers the Taylor series expansion? Thank you, Prof. Okay. The Taylor series expansion, hopefully, we'll see later on. I'll go over it in terms of helping you see the discretization using the Taylor series expansion. But suffice it to say that, depending on your finite difference solution, simulation will be accurate depending on your order of differentiation, okay? Such as whether you are using second order upwind scheme, you are using central differences, and so forth for the finite different methods. In general, higher order numerical methods usually predict higher order of accuracies. But here the problem is that they are basically unstable due to less numerical dissipation. Okay? What do we mean by temporal derivatives? Temporal derivatives are time-dependent derivatives. Okay? In your momentum equation, you have time-dependent derivatives. Or in general, if your problem is transient, that means that you cannot neglect the rate of change of the quantity with time. And so you have temporal derivatives. They can be integrated either by the explicit method, and these explicit methods are the Euler, Runge, Kutta, and the explicit methods, that is the beam warming methods, and so forth. I think in your numerical class, you must have talked about the explicit and implicit methods of solution of these numerical solutions. Okay? Any comments or questions? Okay, so this is just expressing how to discretize your differential equations. And by that, I go back to my Navier-Stokes equations, and I'm saying that, this term, this partial derivative has to be discretized. I can discretize it using finite difference representation, using finite volume representation, using finite element representation. Same for all these other terms. If I use a finite difference representation, for example, then I'll use a Taylor series representation. The Taylor series representation can be, for example, a forward difference, okay, a backward difference, or a central difference. And I'm saying this without writing it, so it may not sink in. Later on, I will demonstrate that, okay? So all these has to be discretized. The discretization results in a set of algebraic equations that you have to solve. Okay, so that is what we are talking about. Now, if you are discretizing using an explicit method, okay, we are saying that explicit methods can be easily applied but yield conditional stable finite difference equations which are restricted by time steps. Okay? What we mean is that you have to be careful in using an explicit method because it only gives you a conditional stability. If you use a large time step, okay, let's say that you are solving your problem for 1 hour. Well, in my solution, my delta t could be 1 second or 1 minute, or maybe even 5 seconds or 5 minutes. Depending on what you set as your time step, that would impact the explicit solution. It gives you a conditional stability. Your solution is not stable. If your solution is not stable, that means that your solution is not going to converge and you're not going to get a solution. You're wasting your time. All right? On the other hand, implicit methods are unconditionally stable, but needs efforts on efficiency. So implicit methods of discretization does not have the problem with time step. Okay? You can set your time step as small as you want or as large as you want, and you're okay, but it affects efficiency. So remember, if I set my time step at 1 second versus 5 minutes, in terms of computational time, which one do you think is longer? A delta t of 1 second or a delta t of 5 minutes? Which one is longer? A delta t of 1 second in terms of how long it's going to take you to get your final result. If your delta t is 1 second versus a delta t of 5 minutes, which one is longer? 1 second is longer because that means that for each 1 second, you are calculating a solution of for each 1 second, you are solving the complete set of your algebraic equation. Okay, so, if you are solving it for 1 hour, how many seconds do you have to solve it? That is 600, right? Now, versus 5 minutes, then you're using a larger delta t, so it solves a shorter time, but then, there will be differences in terms of the accuracy of the solution, but it's conditionally stable. Okay, that is what we mean by this. Okay? Now, usually, higher order temporal discretization is used when the spatial discretization is also of higher order. Okay? In terms of stability, a discretization method is said to be stable if it does not magnify the errors that appear in the course of numerical solution. What does this mean? In other words, if I'm solving the problem using explicit method, and I am restricted by the time step, if I don't select the correct time step, then that means that it's going to magnify the error in my solution. Okay? It's going to magnify the error in my solution, and I will not get the right results. Okay? So your solution will not be stable. Okay? Will not converge with time. Okay? So that is what this is saying. Yes? A small time step should yield a better accuracy than a larger time step. That is the ideal case. Now, the penalty is the computational time or your computational resources. If you have a very huge computing system with a large storage space, then you can afford to do that. Okay? If you have a supercomputer, then you can afford to do that. Now, preconditioning method is used when the matrix of the linear algebraic system is ill-posed, such as multi-phase flows and flows with a broad range of Mach numbers. Okay, so when you assemble your matrix for the discretized domain, you can end up with an ill-posed matrix. Okay, some matrices are so nice, so beautiful that you can use a standard algorithm, okay, such as the Thomas algorithm, which is a tridiagonal matrix solver to quickly solve the problem. But if it's such that you don't have a well-structured matrix, then you have to do some preconditioning, okay? And that is a numerical trip that you have to do. And here it's saying that this preconditioning is required particularly when you have multi-phase flows and when you have some problems that are compressible because of huge Mach numbers. How do we define Mach numbers? Yes. Thank you. All right. So I'm just seeing whether I'm saying some terms and whether you relate. Selection of discretized methods should consider efficiency, accuracy, special requirements such as is going to flow like a nozzle. Okay? In a rocket nozzle, the fluid is going to flow through an inlet with a diffuser at the outlet. Okay? Well, in order to analyze the flow within the nozzle, we have to construct our grades. Note that, you see, since this is not a straight line, if this was a straight line, then we can easily construct this equally spaced grade with the same delta x as delta y. Okay? Delta x is the distance from this point to that point, and delta y is the distance from here to there. Okay? So we can really get the same delta x and delta y. But because of the curved nature of the outline outside of the flow channel, we cannot easily get this. We can only get this form of equal distribution of grade if we transform the y coordinates to the y-x coordinate to this new coordinate system. Okay, eta and psi. Okay, so we have to do a coordinate transformation. This is the physical domain, and this is now the computational domain. So we do the transformation between the physical domain and the computational domains by basically doing this transformation using these partial derivatives. To do this transformation, that means that you have to know the equation that represents this curve. Okay, this curve is a function that is varying depending on x with y as your dependent variable. So I'm saying that if I take that function and take the derivative of f with respect to psi here, and psi with respect to x, and f with respect to eta, and eta with respect to x, you can obtain a transformation of this grade to that. And we do the same for the y direction. Okay? So, yes?
Because you want a structured grade?
Because I want a structured grade, yes. Grid points are the points of calculations, but your computational domain has to be gridded, right? So we are saying that, well, you know, this is not a uniform outer layer, okay? So in order to get to this computational domain, we have to do some form of a grid transformation. Otherwise, the other approach would be say, well, remember, if I cannot use a structured grid, I can use an unstructured using a finite volume or finite element. Okay, so yes, I don't have to do this transformation, but I can use a finite volume or a finite element to solve the problem. Yes?
So in that case, with the computational domain, will that one have a kind of higher accuracy than the one using the finite kind of computation? If you are looking at the two, which one will have a higher accuracy?
Okay, so the question is, once you do this transformation, will your results be the same in terms of accuracy? And the answer is yes, because once you obtain the result in this domain, you have to transfer back to your original domain. Okay? Yes, every point in here will map into a point over here. Okay? And of course, the numerical accuracy basically depends on how well you do this mapping. Okay? But the results from here can be mapped back into your actual physical domain. So, you know, we are able to use numerical methods to solve our problem, playing all sorts of tricks with our grades. Now we get some results. So even the results give us wahala. How do I depict my results to clearly understand, what I'm seeing? Okay? And so, yes, there are post-processing softwares that you can use to even represent your result. You see, this figure is an isosurface of Q300 color scheme piezometric pressure. In other words, it's a surface showing the pressures at various locations. Okay, showing pressure at various locations. Now, this is two forms of representation. Okay? This form is more enhanced than that. So here, in this enhanced form, at the wake here, you can see clearly, some of the pressures in the different regions. Let's say assuming that the darker regions means the higher pressure region. Okay, over here, you cannot see the pressure gradients clearly, right? Because all of them look red. But whereas if you use this more enhanced post-processing system, you can see the pressure regions a bit more. Okay, and so yes, you can visualize CFD results. That is whether it's contour, velocity vectors, streamlines, path lines, streak lines, and isosurface in 3D, and so forth. And you can use a CFD user analysis, verification and validation data to further analyze your results through post-processing, commercial softwares. Okay, those are available for you to analyze. Well, so far to this point,